Today's the 11th. This is 12:30, 1:45. All right, hello, Oscar, Alicia, Amina, and Louisa. And hello, Chelsea and Penelope. And hello, Feeny and Bella. Good. While we're gathering up, go ahead and find your questions, folks. So anything at chapter 2 or 3 you'd like to ask about. Hello, Ellie. As we will begin with you today, and then we'll continue with solubility. So chapter 4 in a little bit. Sorry, I'm so far away. It's hard to be at everything in my 1 square meter studio here. Okay, good. I got 9 of you. Let's get a couple more, and then we'll be ready to start up. There's Antonin. Super. Couple more, and we got everybody. That would be great. Okay, let's just put that aside, and I'll check people in as they say hello. Oh, there's another one. Lola. Hello, Lola. Good. My people, do you have some questions you'd like to ask about that we could strategize together on in our big Chem book 2? If you do, give me a page, give me a number. There's Anne-Sophie and Arrow. By golly, 2 to go and we're there. I still need Aiden. I still need Alex. So I'm missing a couple of A's. Aiden and Alex, if you're out there, say hello. Ute. Okay, in the meantime, any you want to ask about, this is your opportunity. Please let me know. See if you've marked any pages of some you can't get or would like to know how to do. I assume you're working a lot of these by talking to each other, which is good. I know you've got the answers, but sometimes it's hard to know how they get to the answers or why. So if any of those things are bugging you, now's a good time to talk about it. All right, I'll give you about 1 more minute to think. And then we're going to start up because we got lots we need to do. Okay, I tell you what, let's start up this way. If you think of some questions, fine, but let's begin with a warm-up. MgCl2 solid dissolves in water. Draw a picture or diagram showing The interactions with water. What do you suppose they want you to do for that? So, draw a diagram showing interactions with water. Oh, and I got lots of comments now. All of a sudden, let's see. How do they know how to draw the graphs? For example, page 110. Okay, I can look at that in a second. And I'm not sure the y-axis distance is something that we need to necessarily know how much that shift is, Amina, but we can look at one a little bit. Okay, back to my question. So we'll come back to Amina's in a moment. For now, so this dissolves in water. What's it going to look like? Because chapter 4 is about solubility. We've done this before. Some of you got it right. Some of you got it very wrong, which is why I'm asking it again. Okay, I got MgCl2 dissolves in water. What's the interaction going to look like? Well, let's start with the water. Okay, so here we go. Boom, boom, boom. Let's let that be my water. Okay? I'll do a little symbol. That's water. This is dissolving in it. Help me with my picture. Please help me with my picture. All right. While you're thinking, no, actually I can't. I need your help now because it's going to change how I do the rest of the drawing, won't it? Let's say I need 8 waters and 1 unit of MgCl2. Okay, so Amina says I got Mg2 plus and Cl minus. Good. Somebody else, what goes where? Everything separates. Good. Now, what goes where? I know they separate. What goes where? Which side of the water has what charge? Okay, so the small ends will look at Cl minus. Good way to say it, arrow. Okay, so let's do some colors because why not? So let's say that is my Cl minus. And my Mg plus better be smaller. You now, my AP students, have to know that. Cations are smaller. They're pulled in, right? They have less electrons. Good, now we're getting some more comments. Let's see what others have to say. First, I'm going to draw something that Arrow said. So he said the small ends will look at Cl minus. So the H ends, that's the positive side. So that's going to look at Cl minus. So I'm going to do this. Let's see if I got another one. Okay. The Hg will face towards the Cl minus. The H's will face. Yeah, okay, that's the same thing Errol said. Thank you, Chelsea. Aiden is here. All right, you got to say hello. Do I have Alex? He's my last one missing. Okay, Aiden says the Cl minus will go to the H plus, and the Mg2 plus will go to the O minus. Good. Okay, so let's not put that on there. Ready? So we got to go Mg. Whoops. Where's my symbol for it? Now look at what it says. I need a unit of MgCl. Well, and I need 8 waters, so I got to have a whole lot more waters, don't I? So I'm going to put more waters around, let's say this one. Let's do what Arrow said and have the small ends, the H's, pointed towards the Cl minus. And it also says I want a unit cell of this. That means I need another Cl minus in my picture, don't I? Because it's MgCl2. So I need another one. I'm going to put one over here. And I'm going to put some more waters because I'm supposed to have a bunch of waters. So let's do this other one, put another one maybe over here. And another one over here. And put some other ones over here. How many I got? I got 6. Let's add a couple more over here. So there we'll follow the rule that several of you said, including Amina and Errol. So I got these puppies, the positive sides facing this. Can you all do that? The answer needs to be yes for each and every one of you. This is an essential understanding of what it means to dissolve and what it looks like once they dissolve. This is now inside here, we've got ion dipole interactions. I don't have to write those in, but if I did, I would say that's where they're happening, right? In between these, I've got ion dipole. Well, let's say what they are. They're not interactions, they're attractions between particles, right? So you should know that term, and you should know that that's how your picture's got to look. Questions about that? If you could have come up with that, you'd get a point on the AP. Almost every year there's a drawing like that. Okay. Do we have to label the charges? You don't have to. You can, Feeney, if you want. But I did label them over here, and that's adequate. But if you feel like you want to do this and write 2 plus and minus on the CLs, you can. Or you can even put it inside, whatever you want to do. It's kind of up to you. As long as you have a key so people know what you're doing. And sometimes they even give you the key. Then they just want you to like use the key to make a picture. Let's see if there's any other comments or questions. We're going to go back to Mina's comment in just like right now. Okay, before I do anything else, and I'm going to mark my page, so we'll come back to it. Let's take Amina's question about these diagrams on page 110. So everybody turn to 110 for a minute. We're going to go back in chapter 2 and think about these. So the question is about page 110 diagrams. Okay, for example, and I'm assuming 111 as well. So, because 110 doesn't have much on it. Are you thinking about also page 111, Amina? Oh, no, you got a specific question. Yeah, 110, number 3. Okay, so here we go. Look at that. Let's do this. Okay, so number 3, everybody. And I've got to look at the whole problem. Nope, 3 is separate. Okay, look at the graph below at T1, and more H2 is suddenly added to the closed system as shown. Okay? Equilibrium was reestablished at T2. Okay, time T1 and T2. Okay, this is not the same as the diagram over on page 111. So I've got to kind of look at what she wants. This to me looks like I want a concentration over time diagram. So there's no label here on the left side, Amina and everybody else. So we're just going to like guesstimate. Okay. All right. Let me make this thing. Okay. So they got the starting concentration. I see what they're doing. So at T1, this is what they do. Okay. So we're going to do concentration, and we'll make that T1, T2. Okay. Molarity. Let's do the I2. So at T1, more H2 was added. Okay, so here we go. There's H2. And suddenly they say more is added. Okay, well, what's going to happen, gang? If more is added, how's that going to shift the reaction? Towards which side? Which side will be favored, or it'll shift towards which side of the reaction? I'm looking at the reaction in number 3, page 110. Which way will that reaction shift? And Amina said it to the right. It'll shift to the right. Amina, she said it herself. So it'll shift to the right. It'll shift towards the product side. Thank you, Alicia. Exactly. So what that means is I've got an initial bump, but then it's going to come back down. Now, I would maybe just show that going like this. It's not going to come back all the way down where it was. Remember, the Chatelet's principle means a reaction adjusts to partly compensate for what we do. We put a bunch of this in. It's not going to be able to get rid of all of it, but it will partially compensate so that ultimately, here's my T2. We're going to hit equilibrium somehow, and it's going to be a higher level. Did I show that very well? Not really. It's going to be higher than it was over here, okay? Something higher. You know what I'm saying? So it's going to start out here, and it's going to go higher. Let's do the other one. Okay, HI, the happy product. So HI is here. What's going to happen to the amount of HI based on what Chelsea said, and Amina and Alicia? What's going to happen to the amount of HI? That's your product. What's going to happen? Okay, good. Thank you, Oscar. It's going to increase. So let's have it do that. And so I'll make more of it. And I'll probably have it end up at equilibrium at a higher level, like that. So I'm saying at T2, we're going to have equilibrium again. That's kind of my thinking of the problem. And notice, I mean, I'm just doing some amounts. I don't know how much, okay? Finally, let's do the I2. And that starts out up here. I got a lot of that. Well, what will happen with that based on the shift that you guys said? What's going to happen to the concentration of that sucker? What will happen to I2? Thank you, Penelope and others. Good. So it's going to decrease. So here it goes. And it's going to be at some lower level and then reach equilibrium out here. Okay? So that's kind of how I do it. Amina, did that help answer your question? Because you don't have any exact numbers for this, and you won't if you're given something like that as an AP question. And it might very well be, Amina, like a multiple choice question that something like that would come up on. Okay? Good. And don't their changes need to be proportional? Yeah, probably, Isabella. I think this one it's all, yeah, probably it would be proportional. Thank you, Isabella. So let me look at that again. So HI, so it's twice the HI. Good going. So if it's twice HI, then it'd be 1 to 2. So maybe HI would be even higher. So let's see. I had it go up like that. Yeah, it'll be something higher, I think, than I have it. But I don't think it's that big a deal for this one. Again, you can't really know the amounts, but Bella, you're probably right about the relative amount. It would certainly be greater than the increase. Whatever HI increases, it's probably going to be. Okay, I didn't really write that very well. Let's take Bella's consideration. Okay, the equation says I got H2 plus I2 forms 2HI. That too, she's probably right. So let's adjust it. with her good suggestion. So it's going to go up. Maybe it's going to go up actually twice as much as I got. So let's have it go up a fair amount. How about we have it go up like that? So we had this go up that much. I'm trying to kind of see. I had this go up that much. So maybe I'll have mine go up twice as much. So maybe it will even look like this. How about this? Is that your thinking, Bella? So it's like twice as much up as this one went up, relatively speaking, because of this factor of 2. So we made that much, much higher. I don't know what the book has for an answer, but let's see if that was. Thank you, Bella. Very good suggestion. She's right. She's right. Good. Other ones we want to ask about in chapter 2 or 3? I will do 2 things, by the way, while I'm waiting for you. I will, in the future, release the units 3 and 4 review questions in the AP classroom. I know some of you are ready for that already. And I'm going to make up another quiz, and I'll tell you about that probably next week. I'll probably have it due a week from tomorrow. And the quiz will be on probably Le Chatelet's principle and equilibrium. So we should do one on chapter 2. That's what I'll do a quiz on for next week. Okay, question from Bella. Do the lines at T2 come together? No, I'm not trying to do that. No, they just go straight there. Once they hit equilibrium, Bella, they should just be straight. If I wasn't such a slob, that's the way they would be looking. The answer key had it how you originally drew it, just that the H2 and the HI lines were closer. But HI was still below the H2 line. Okay, I wouldn't worry about it too much, Amina. Like I said, I think because they don't give you any mounts, it's not going to be really fair on the AP for them to do that exact type of problem. Again, I think you're going to see it on multiple choice question. And if there's amounts, then they actually have to give you amounts, and you can figure it out with like an ICE table or something like that. Okay, other questions from you? Good questions. Chapter 2 or 3. Anything else you want to ask about? This is why we're here, people. Can I ask all of you a general question? Okay, I did the last broadcast at school. Is the quality here better or not? In other words, is it better for you if I do this here in the basement, or better for you if you can see me walking around the big classroom at school? Which do you prefer? Which do you prefer? Okay, got one that was the same. Any other preferences? So it's easier to take notes from the big blackboard at school, but the Wi-Fi was kind of crappy. Okay, so same from Antonin, the Wi-Fi wasn't that good. Connection here in my basement is better. It's better at home, thank you. Yeah, exactly. Sometimes, Anne Sophie's right. I'm going to do demos and stuff there. I have to do it there anyway because I can't do them at home. The connection's worse at school, thanks, Aiden. They're about the same for a couple of you, including Arrow. Okay. Okay. All right. Thank you. All right. That helps me. Okay. Good. Then let's proceed. Unless you guys got other questions for me, I'm going to raise this and we'll move on to chapter 4 stuff. that over here. So I guess I never got Alex here. So that's the way it goes. Okay, let's begin with some more chapter 4 stuff. So it's on solubility, and just so you know where I'm starting, today I'm going to kind of roll through the book notes and follow her, because they're as good as what I've got. So I'm on page 223, if you'd like to follow along. And she says solubility is defined in a number of ways. Solubility is often the amount in moles per liter, but can be, grams of solute. Remember, that's the stuff we put in per 100 milliliters solution. And notice I could change grams to moles and then divide by 0.1 liters, and I'm right back here at moles per liter. So I could always change this to moles per liter. And occasionally you get grams per milliliter, which again, you can change grams to moles, divide by 0.001 liters, and still change it back here to moles per liter if you needed to. ppm, parts per million, I don't think you're going to get that often. So I'm going to kind of leave ppm out of it, okay? All right, but that you need to know. Okay, so I'm going to take some of their data and I'm going to change the question. Okay, all right. So, sorry, I'm fiddling around here. Okay, I think best how to do this. Okay, let's take that. Solubility. Okay, so, all right, this is not that interesting. You can do these. Yeah, solubility, oh man, thank you. Thanks, Aiden. Solubility, as it should be, right? Okay. Let's take this. Example. Solubility of MgCl2 is 0.87 molar. What mass of MgCl2 is dissolved in 700 milliliters? Let me read that again, and then we're going to try it out together. So it says solubility of MgCl is 0.87 moles per liter. I just made that up. Don't take that to heart. What mass of MgCl is dissolved in 700 milliliters? Okay, Cheryl does this in parts. I like to do it pretty much all as one thing to save time, and I'm going to show you that now. So here we go. Always begin, I'm going to do a little plan to help us think about it. Always begin with the single amount. 0.87 is moles per liter. Don't begin with a double label. Begin with an amount that you can hold in your hand. So I'm going to begin with milliliters. Eventually, I want mass, which is grams. So I'm going to go milliliters to liters to moles using this. and then to grams. So I need 1, 2, 3 steps, and that's how we're going to do it. But you know what? You guys are AP students, so I don't have to do that. Let's get rid of this, because you know that 700 milliliters is how many liters? And we're going to skip the first step. 700 milliliters, please somebody punch it in. How many liters is that? I want you to be able to do that mentally. Thank you, Aiden. Thank you, Penelope. So 0.700 liters, just to keep sig figs. I put a couple of zeros on there. Now I've got two arrows, so that's going to be 2 of these guys, these little conversion factors. So times. And then we get what we got, right? Then we get what we want. Okay, so here we go. Liters, I'm going to get rid of liters and put moles. I'm going to get rid of moles and put grams. Can somebody look up, please, the molar mass of this? All right. So look up the molar mass. Somebody else, what do I put here? Moles per liter. What goes in this spot? What goes in that spot? Moles per liter. If you see it, punch it in real quick. Yeah, I got somebody saw it already. That's cool. Let's see if some others figure it out here. Yes, I do. Thank you. Good. A lot of you. Good. So it's the 0.87 moles per 1 liter. And did somebody get the, Chelsea, you're on the ball. Thank you, ma'am. That's the molar mass of MgCl2. Can someone else verify that? Thanks, Anne-Sophie. Good. Can someone else verify the molar mass that got the same thing as Chelsea for MgCl2? I need us to check that chemical. You can look on the back of your book. But I think it's right. 95.2. And others got it as well. Thank you for checking. Good. Punch it out, please, and let me know how many grams that is. Notice, everybody, liters cancels, moles cancels. I really will end up with how much mass in grams. When you get it, let me know. And onward we will go. Okay, so I got 57.97. Good, let's round it. Look at the number I gave you. Well, actually, to be honest, I gave you 3 sig figs, and here I got sloppy and gave you 2. So what do we need to round that answer to? Probably to 58, probably without even any point. 58 grams MgCl2. Right? 2 sig figs because I gave you 2 right there. Yeah? Okay. Any questions on that? That's kind of a review. We did stuff like that early in the first semester. Okay. I'll leave a little bit of it in case you got a question on the math here. Okay, page 228, which is section 4.2, should look really familiar. You did it already. It's on qualitative analysis. What lab did we do this on? What lab? Check out page 228. What lab, or 229 really, what lab did you use this stuff on? Do you remember? Remember when we used to like meet in person? What lab was it that we used these rules on? Might be one I haven't even been able to hand back to you. Precipitation lab, yes, but it had a different name. And so used on the 6 solutions lab. Qualitative means discussing, just like you had to do for me, where you said, well, this one precipitated with this one and this one, so it has to be Ag plus. This one precipitated with this and this, it needs to be MgCl2, and so on, okay? Exactly, you had to identify the different chemicals, Aiden. That's the one. So you're going to use the same rules and more or less do that again in this section. I don't think I necessarily need to go over that. I think I'll wait till you do some, and then you can ask me questions if they don't go really well. Over on page 233, she uses the term selective precipitation, and I want you to know what that is. It's not hard. So selective precipitation means precipitating out usually as one cation leaving others. This is quite often done in labs in chemistry. If you got a bunch of chemicals mixed together and you don't want them mixed together, maybe you have something poisonous. If you do, you want to precipitate that out and get rid of it. Or maybe you have something worth a lot of money, like gold. Then you want to precipitate that out, and then the other stuff you don't care about. So selective is exactly what people often do in the real world to get chemicals that they want, often metals. Often metals. Good. Okay. We're ready for some actual good meaty stuff here now, unless I see any questions. Okay, I'm going to erase that and continue right below here. Remember, what I'm doing is I want to introduce these ideas to you so that when you do the book reading and problems, you have a little background. So now I'm talking about page 241, which is on solubility. I'll try and spell it right this time, thanks to Aiden's reminder. Solubility product constant, which is K, capital A, with a small sp. Let's see what the heck that is, okay? Frankly, don't get all too worried about it. It's just another products over reactants. So KSP is still products over reactants. But now I'm going to do something funny. You ready? You'll see why I'm doing this. It's still products. Oh, put a single line through over and reactants. And now let's write why. But the reactants, or reactant usually, is a solid. So it doesn't get actually put into the expression. Okay, so it's called a solubility product because you're only multiplying stuff. You're not dividing anything because the reactant is a solid. Let's do one, and I think you'll see what I'm talking about, okay? So, for example, let's do K2CO3. Okay, this chapter is all about stuff dissolving. And remember, it's dissolving in water. And remember, you don't ever put plus water, okay? Because it's a solid. On the other side, it's aqueous. So you're set there. Okay, here we go. I get 2 of what plus what? Can you fill in the blanks, please, so I know you're all out there and understanding? So if this is dissolving in water, I get 2 of what and 1 of what? Because I want to see what you all write. All right, no one has it right so far. Yes, I'm picky. Ah, thank you, Arrow. All right, so he's got the first one, 2K plus. Turns out there ain't no K out there. It doesn't exist in nature. There's only K plus. And that's aqueous, by the way. Plus, let's see if somebody's got the second one. Amina does, as does Aiden and Antonin. So CO3, 2 minus, and that is also aqueous. Beautiful. Now, let's write this. So example, they would say, write the KSP expression. Expression means no numbers, just symbols. So if you're asked for the expression, you got to know you're asked for symbols, all right? Don't give numbers or you don't get the point. So let's do it. So KSP is equal to, and now let's erase a little bit because it looks sloppy. Oh, let's get rid of all that. I think you're with me. Okay, let's see if anybody's got it. Okay, so now remember, yeah, Lola had it too there. Remember when you do it, it's going to be products. So I got to do what? Now I got to do moles per liter traditionally, right? So that's brackets. K plus times. I know it's a plus here, but remember it becomes a multiplication down here. So CO3, 2 minus. And on the bottom, oh, it's a solid. So all I have is a product. Oh, that's why it's called a solubility product. There's no division. Solubility, underline, product. Good. All right, where's my mistake? Somebody find my mistake. Aiden found it. So did Chelsea. Good job. So look at it. There's a 2 there. And notice I forgot it. So I'm going to put it back here. That time I actually did do it on purpose to see who was looking. And you guys are on your game. Good job, Aiden and Chelsea. So there's your solubility product expression, KSP expression for potassium carbonate. All right, so now there's 2 ways to do some problems. Let's see how we're doing. Yeah, we're doing okay. Yeah, good. Okay, that's how to do an initial expression problem. Let's do another one where we ask about find the KSP for, I got to pick an easy one with you. for BaCO3 if the solubility is equal to 5.0 times 10 to the negative, and I got to do some math real quick. Fifth, I think. Molar. Okay, remember, solubility is an amount in moles per liter, unless you're told otherwise. Okay. The way I want you to do these problems is, did I screw up? Do we leave the first problem like that? Yeah, it's done. That's the expression. So that's it, Aiden. You are done. So if they want an expression, that's it. That's the expression for the KSP. That's it. So we're starting a brand new problem. Okay, and this time I'm going to do it for barium carbonate. And I'm just going to tell you the solubility is this, and we're going to find the KSP. Now, we're going to do two sorts of problems. I give you the solubility, you find the KSP. The other one, I give you the KSP, you find the solubility. They're done virtually the same way. All you got to do is follow the boring steps, okay? I don't say that very often. I like chemistry, but these are kind of boring, and I want them to be boring, because if they're boring, you're doing them right. Okay, so first thing you always do is write an equation. If it's multiple choice, then you're going to think that equation. All right, I'm practical. I want you to go fast on the test. But here I'm going to write it because let's say I have to show my work. So I got solid this, and it's breaking down into, and this time I think everybody's get it because we already had CO3 2 minus, and the other one's barium 2 plus CO3 2 minus. And those are both aqueous. Do I want to bother to put that? I will just for this time. Maybe I won't always do that, but those are aqueous. Now, solubility. In chemistry, solubility is a small s. And it's in moles per liter. All right? Why is that important here? Because the S, the solubility, looks like this. Okay, here's my equation. For every one of these barium carbonates that breaks down, don't I get one of these barium 2 pluses and one of these CO3 2 minuses? Of course, the answer is yes. What if I had S of these break down? Then I'd get S of these Ba2 pluses, but I'd also get S of the other ones. Why? Because it's 1 to 1. So if it's 1 to 1, it's S to S. S is whatever number it happens to be. So now I'm going to go slow here. So if you get bored, I'm sorry. I want to write the KSP expression next in symbols, just like I talked to Aiden about a moment ago. So just in symbols. So this time it's easy. I got Ba2 plus times CO3 2 minus. Now we put S into the deal. Look at the problem. So find the KSP if the solubility, oh, they're giving me S. They're giving me S. The solubility is this number. So it turns out this is just going to be S here and S for this one because it's 1 to 1 to 1. So the solubility expression can be simplified to the KSP equals just S times S, or I'll keep it in red, S squared. Okay, let's finish it up over here. Now you got to do is say, but I know what S is, gang. Look at this. The KSP then, that's what they're asking me for, is equal to the solubility squared, but that's just 5.0 times 10 to the negative fifth molar squared. We can probably even do that mentally, can't we? So it'd be what, gang? 5 times 5 is 25. 25 times 10 to the negative 10th. But now I got to change the front number, don't I? Penelope, you are quick. So she's right. It's 2.5 times 10 to the negative 9th. KSP, like the other Ks, remember it's just an equilibrium constant, has no label. So KSP is just that number. And thank you, Penelope, for checking me along with Amina already. You guys got it. Okay? Good. Questions before we do one that's a little bit more interesting? While you're thinking, I'm blowing my nose. Okie dokie. Does Q have a label? I'm not following, Bella. The KSP doesn't have a label, and S is in moles per liter, but the KSP has no label. It's just a number, and it's a number related to 1. Bigger than 1, less than 1. This is obviously not very soluble. Look at the number. It's way less than 1, isn't it? It's the negative 9th power, so it's not very soluble at all. Q heat. Yeah, I don't know. Bella, you're gonna have to like clarify your question because I don't quite get it. Ask me again. In the meantime, I'll look here and see. Yeah, so that's just S, and it's in moles per liter. KSP, no label whatsoever. Okay, good. All right, good. Then let's do another. Ready? Here we go. Please turn to page 245 where you get a lot of data. Page 245 has lots and lots and lots of KSP data. We're going to use that now. You'll need to use that for problems. On the AP test and on my clausur, I will give you the data. You don't have to know it. You're going to be given the numbers. Okay, so let's do, how about PBBR2? Okay, so find, these are all at 25 degrees. So my example will go like this. At 25 degrees C, by the way, most things are, when I heat them up, this is 25, most things when I heat them up, what will happen with their solubility? Can you guess? Most things, when I heat them up, what will happen with their solubility? Before we do this. I heat something up, what happens to its solubility? Most of the time, it's for most solids. Thank you, everybody's right. It will increase, like 99% of the time, all right? Good, thank you, good, just checking. So you gotta know the temperature, don't you? All right, so at 25 degrees C, find the solubility S in moles per liter or molar for lead 2 bromide. Okay, so first thing you got to do is come up with the formula. Somebody can punch it in if you want. goes to what? Lead bromide. Give me the formula, somebody. And you can also find the formula on page 245 if you're thinking. And on 245, I also need the KSP number eventually from you. But first, give me the formula, lead 2 bromide. What would it be? There must be quite a lag time today. There's some. Okay, so PbBr2. Thank you, Chelsea. Right. So PbBr2. Br is minus. I need 2 of them. Okay, remember I said these were boring? You're going to do the same thing that we did in the last problem. Boring. So break it up into Pb 2 plus. And if it's boring, it means you're doing it correctly. Plus 2 this time, Br minuses, right? Because you know bromine is negative, and those are both aqueous as such. Okay, then, and I see that's what someone like Amina had that already. So that's that. Now we want the solubility S. So we got to do some thinking. Okay. Actually, I take it back. Let's do the expression first. So KSP. Products over reactants. Reactants is solid, so just the products. So I got to go concentration of Pb2 plus times concentration of Br minus, and this time I won't try and kid you. It is squared, as several of you caught me last time. Now we got to go back and think about solubility. Okay, gang, for every one of these that dissolves, I get 1 of these and 2 of those. So for every S of these that dissolve, I get S of these and 2S of those. That 2 is going to matter. We're going to use the 2 twice. Watch carefully. I'm going to bring those down and say, well, I'm going to put S here, and I'm going to put 2S here. Okay, so the KSP in terms of S looks like this. It's S times 2S quantity squared. Ooh, you use the 2 times. Once in terms of the amount of ions, twice in terms of the squared, so it becomes twice as important, the 2. Okay, what is that? Do a little algebra for me, gang. S times 2S quantity squared would be? No, Chelsea, careful. Do it one more time. No, Amina, careful. Do it one more time. I caught you both. Careful with your algebra. 2S quantity squared. Yes, there you go. Thank you. Bella has it. And now, let's see if some others had it as well. Careful, Anne-Sophie, you're not adding. You got to multiply still. It wouldn't be 5, but 4. 2 times 2. So we go 2S times 2S would be 2S squared, but that's, 4S squared, 2 times 2. 4S squared times another S, so it's 4S cubed, as Bella said. Are we ever going to finish this problem? Yes. You've done all the hard work. Now we just got to plug in a number. Look, the KSP is on page 245. Find it. One person type it in, or 2 or 3 maybe. Where did the 2S come from? Okay, Amina, back up. It came from up here. I'm thinking 1 of these gives 1 of these and 2 of those. If I dissolve S of these, I get S of these and 2S of those. So the amount of Br minus is really 2S. But I've got to use the 2 in another spot. I don't just put it in for the Br minus, but I've got to square that. So I end up using the factor of 2 twice. in the expression. Here, 2s, and another time I got to square that. I hope that helped. Okay, somebody get my KSP for me? What is it? I need the number. Earth to class. It's lead bromide. Did I pick one that was on the table? Yeah, I did. Anybody find it? There it is. Thank you, Penelope. 6.6 times 10 to the negative sixth, exactly, with no label, equals 4s cubed. All right, now it gets a little mathy, but not much. Do what? Divide both sides by 4. That gets rid of the 4. And then you got to take the root. The root. So you may have to find that on your calculator. It's not a square root, it's a third root, like this. Might be under a math button or something on your calculator. The cube root. Thank you. That's what I'm trying to say, Amina. So please do that and let me know what you get. Then it's just S equals, and can everybody please do that on your calculator so I know you can get the right same answer. So what's the cube root of this thing divided by 4? May have to do it all in parentheses. Okay, I'm going to write down a couple answers and see if you all get the same thing. So from Amina, I got 0.0118. And from Chelsea, 0.02. She's rounded, I think a little too much, unless you guys got different answers. That's a very different answer. Let's see what some others get. They should be closer together than that. Okay, Bella's got 0.02. Okay, Achtung. This has 2 sig figs. 0.02 has 1. So I need to know what that is. Okay, Chelsea's saying it's 0.12. And now Chelsea has it with the right number of sig figs. Yes. Yes. Okay, so let's do it. So I think the answer is just exactly that. To 2 sig figs, 0.012. And now it's solubility in moles per liter. Ba-da-ba-da. Right? So I'm going to put big M on there. Does it come out automatically to that? Yes. S will always be in moles per liter when you're done. Okay, I hope everybody gets that number correct. 0.012 molar for this one, because I'm pretty sure that's the right answer. Okay, so does it get more complicated than a cube or a cube root? Yes, it can. Yes, it can. Let's do a little short one to express that. Questions on this before I go? Were you all able to get this at the end of the day? I hope so. And on the AP, you don't need an answer sentence, but you need it rounded and the correct label on it to show that you found S solubility. Questions before I erase this? So when in doubt, everybody, math-wise, put all this in parentheses, and then whatever your answer is, take the cube root. You all better be able to get this. I know I'm harping on it, but it's a kind of a big deal. Okay, all right. I'm not seeing any questions. So let's hope you get that. So I'm going to say now, I'll just give you the chemical to save time. FeOH3 write the KSP in terms of S. Maybe that's the whole thing that they want. They don't even want a number for it. So let's start out and make it boring. Ready? Boring. FeOH3 solid. I know. Pinch yourself so you stay awake. I know it's boring. I don't say that for many parts of chemistry. Okay, so I get what? Fe with what charge? Who's following? They didn't tell you which Fe, but you should be able to figure it out. Fe is what charge here? Just seeing if you're still with me. Thank you. Thank you, Anne Sophie, and Aiden, Penelope, and others. Good thinking. So this time it's 3 plus, and then I got plus 3 OH minus. Do the expression. KSP equals, I'm just going to write it because you've done enough of these now. The interesting part's coming up at the end. OH minus to the third power. Now play the S game. Boop. Yeah, if S of these dissolve, I get S of these, and I get 3 S of these. Can that really happen? You betcha. So now put in the S's down here. So this is really S will go here, and now I got to put 3S here. So the KSP, look at my question. I want the KSP in terms of S. Let me stop and see if you can do that now. You ready? Who can do that? What will be algebraically now the expression in terms of S? Amina, you're quick. Check your power on your S. Yes, check your power on your S. I don't have a perfectly correct answer yet. So think of how the algebra is going to go. Now I do. Okay, so let's see. So I've got 3S quantity cubed. You've got to cube the 3 and cube the S. But I got another S over there. Don't forget about that. Thank you, Alicia and Aiden. So you guys got it. So 27, 3 times 3 times 3. S to the third times another S is S to the fourth. Voila, you're done. That's all they wanted. If you had to solve for S, you'd have to divide the KSP by 27 and then take the fourth root. Occasionally it happens, but it's unusual. Okay, on the AP, not so often. Yeah? Okay. We get something more exciting, and I think it's coming up. Yeah. Thank goodness. Whew. Okay, now we get to play an actual game for the last few minutes, okay? We'll at least start it. Let's see, do you got any questions here first? Because the game is much more fun than what we've just been doing, and much more interesting. But I often do it as like a game show if we're in class, but you know, pretend I'm on your television. Kinda I am. Okay, so it's time for everybody's game. Will there be a precipitate? Everybody's favorite game. Yay, hooray, woo! Here's how to play. You find the solubility product. Yeah, I have to use the 3 twice. Same reason, Anne-Sophie, I used the 2 twice in the other problem. It has to be used in 2 different spots. Okay, will it precipitate? Here's the philosophy. Find your solubility product. Is it greater than K? KSP? If yes, you got to precipitate. If no, you don't. We're going to at least start a first game here in the next few minutes. Yeah, so it's for the last one, it's 3 times 3 times 3. You got to cube the 3, Aunt Sophie, as well as the S. I can't leave the 3 out. Okay, so let's play the game. You need to be able to look back to the page with the KSPs, just as a warning. And by the way, if it's equal to, so if equal to the KSP, then it's called a saturated solution. It's got all in it without precipitating that it can have. Saturated solution. Okay, that's a little aside. Okay, we're ready to play the game. And I got to pick a precipitate here and just see. Okie dokie, let's do lead chloride. Okay, so example. If 1 liter, well, let's make it 1.00 liters, contains a concentration of Cl minus equal to 0.017 molar, and a concentration of Pb 2 plus equal to 0.14 molar, will there be a precipitate? Okay, same stuff, and I'm going to do this fairly quickly because we're running out of time. All you do is the same darn thing again with one little difference at the end. Okay, so we go, what, Pb Cl2 goes to Pb plus 2, sorry, Pb2 plus 2 Cl minus. Then I got the KSP expression, which is Pb, oh good gosh, Pb2 plus concentration times Cl minus concentration squared. That should all be reviewed. But now we got to put this in and see if it's equal to more or less. So now I don't know if it's equal. Okay, the KSP number, you ready? I'm going to look it up for you to save time. Lead chloride, it's 1.2 times 10 negative fifth. 1.2 times 10 to the negative fifth. And now you got to do this and compare. You got to drop in the 0.14 molar times 0.017. I know I'm getting to the bottom of my little screen, squared. And before you go, let's punch it out. Is it bigger or smaller than the KSP? That's what we got to know. So I'm going to move to the top here. So that's called my solubility product. Okay, so solubility product is, maybe somebody can punch that out. Several of you got it. Okay. No, the thing in parentheses. What? If one that contains would it be specific? Yeah, exactly. Yeah, I use here I don't need to use the 2 twice, Aiden. I just got to go Cl minus. I know the concentration. I just got to square it. So square that and then times the PB. So I got to go 0.017 squared times the 0.14. And somebody let me know what you get. Can't read at the bottom. Okay, so let's try it again. Here we go. So there you go. So I got a KSP as PB2 plus times Cl minus squared. And then putting in the numbers, it's 0.14 times 0.017 quantity squared. And I need somebody to punch that out because we got to see if it's bigger or smaller than the KSP. 1.2 times 10 negative fifth is the KSP from that page in the book. It's 4.05 times 10 negative fifth. Okay, so Chelsea has it. 4.05 times 10 to the negative fifth. And that is, it's bigger. That's bigger than the KSP. So it's bigger than the KSP, which was 1.2 times 10 to the negative fifth. So therefore, the solubility product, 4.05 times 10 to the negative fifth. It's the same power, but it's a bigger number. So yes, there's a precipitate. Woohoo! Glory, hallelujah. That's how the game is played. We just played the easy version. We'll play a harder version, but more interesting, next Wednesday when I see you. Okay? Because Monday is really a holiday. I screwed up last month, but I'm pretty sure we don't go to school Monday, so I will have you first Wednesday. Okay? Thanks for staying with me the extra couple of minutes. All of you wishing you well, stay healthy, and I'll send this to you in case you need it via the class stream. What does it say in red? It says, if KSP, then saturated solution. That's the red thing. Okay, thank you all. Bye.